We are now moving to Professor Gutin. I have his presentation in the PDF file. I'm going to try to share. It's always those challenging moments, isn't it? Okay,
yeah.
Here we are.
Right.
Okay.
Well,
okay.
Not the first page, of course.
So if you can give me the opportunity to introduce Professor Gutin. He's a member of the Academia Europaea. He's also a professor of Computer Science, Department of Computer Science, Royal Holloway, University of London. So the floor is yours, Gregory.
Right, thank you. So, right.
Just let me know of when do I need to move to the next page. So,
well, could you please go to the first page here? Yeah.
Yep.
To the
Okay.
first page.
Mm-hmm.
Yeah.
Let me try to see.
Yeah, it's
Where
it's not that far. So yeah. Thank you very much. Okay. Yeah. So So it's I'm going to speak about parameterized algorithmics and access control, linking theory and practice. Access control is a special branch of information security. Yeah, next page, please. Now, as you can see, I'm planning to cover a lot of ground. I'm not sure in 20 minutes I can do it, but I will try. Okay, next, please. And next, please. So a workflow satisfiability problem. So this problem is of interest. So it's one of key problems. In fact, in access control, for example, in 2015, there were 2 papers which received Best Paper Award in DBSEC, Database Security, and SACMAT Symposium on access control. So, and the Best Paper Awards were for papers on WSP. And so there are many variations of this paper, but many can be reduced to the basic WSP, which are actually the main topic of most of the talk. So what is it? I mean, let's consider a WSP instance. So we have, say, 4 users and 6 steps, and you can see what these steps mean here. So S1 is create purchase order, S2 approve purchase order, and so on. So it's a small WSP instance. So next, please. Okay, so now you see, apart from these users and steps, we have constraints. So we have constraints. First of all, you know, not every user can perform every step. You see below each step on this diagram, just users which are allowed to perform that step. For example, S1 can be performed by U1, U2, U3, S2 only by U2 and U3, and so on. Now, also some binary constraints. In this case, you see equal or non-equal. What they mean basically is the same user must perform steps S1 and S3, but different users must perform steps S1 and S2. And as you can see, we have several such binary constraints. So now, is there a solution for this? Whether we can assign the users to the steps? And the answer is yes. And now we here not only the answer is yes, but we can see what it is. So user 3 is for step 1, user 2 is for step 2, and so on. So and all constraints and authorizations, they are satisfied. So now we can go to the next page and look at the general formulation of this problem. So here we have a set of steps, set of users, and 2 types of constraints. Constraints in C family of non-unary constraints. So it's binary or higher arity constraints with variables S and domain U, and unary constraints. They are called in access control, they are called authorizations. And so they assign, as I say, for every step, some subset of users, so which can perform it. Now, so what we are seeking is a plan which maps steps to users, and the plan is valid if pi satisfies all constraints, binary and non-binary, unary and non-unary, and the instance WSP satisfiable if there is a valid plan pi. Now, what is our assumption generally here is that in polynomial time, we can check whether a plan satisfies a constraint, which is a practical assumption because otherwise otherwise constraint is not practical somehow if we need so much time to check it. Now, basic WSP is essentially constraint satisfaction problem. The well-known constraint satisfaction problem, where constraint satisfaction variables are WSP steps, constraint satisfaction values are WSP users, but in this talk we are going to speak about WSP. Now, of course, there are less basic WSPs, for example, those which use parallel branches, release points, and so on. And I mean, there are two papers which are listed here with my participation, but there are others which basically where non-basic WSP is considered. But I want to again to stress that we can often reduce less basic WSP to basic WSP, like in these two papers above, and therefore we will focus on basic WSP most of the talk, of this talk. Next, please. So what was basically noticed in a paper of 2010 by Wan Li is that in practice the number of steps is much smaller than the number of users, and more than that, the number of steps is usually relatively small. And so Wan Li, as I said, that's the paper I mentioned. So it's in the Journal of Transactional Information System Security. They said that because K is small and much smaller than the number of users, then we should consider parameterization of the problem by K, because it's a small parameter. And the problem, and they ask whether this problem is fixed parameter tractable, namely whether there is an algorithm of running time where the coefficient of running time might depend on K, but the rest of the running time is simply a polynomial in the size of the problem. And they also showed that unfortunately it's not, because they showed that the problem is W1 hard, which roughly corresponds to NP hard for classical complexity. So on the other hand, they considered some special case of binary constraints, and for them they showed that the problem Fpt, when these binary constraints are like that, unary constraints on the other hand are arbitrary. So now we moved on with this research. We thought it was very interesting, and we tried to go on further. Next, please. And so in our paper of 2014, we introduced user-independent constraints. So there are constraints which don't depend on the identities of users. So formally we can introduce them as follows: that constraint C is user independent if for every plan pi from S to T, from S to U satisfying C, there is a permutation. If it satisfies C, then for every permutation, if you take a permutation theta of u, then plan pi prime also satisfies C, where for every step we simply permute it according to this theta. Now, counting constraints are basically of two types are user independent. The first one says that for a set of steps R, a set of steps Q must be performed by at most R users. The second one says is that a set Q of steps must be performed by at least R users. And so first type is security, gives you a security requirement. The second one, diversity requirement. And an example is basically all diff. So all basically users for steps in Q must be different, and they are all often used in constraint satisfaction. Now, what is interesting about user-independent constraints? All the non-unary constraints defined in 2004 American National Standards Institute role-based access control standard are user-independent. So we basically identified a set of constraints which are of practical interest. Now, what we showed actually that for this set of constraints, if all non-unary constraints are user-independent, then we can solve it in fixed parameter tractable time, which is 2 to the power of k log k. This O star means that we don't put any polynomial coefficients here. So we take only exponential part of the running time, depending on k here. And so we also showed that unless so-called exponential time hypothesis used a lot now fails, no much faster algorithm. We cannot do it faster than we cannot do it in 2 to the power of O small of k log k time. And what is ETH? ETH says that 3SAT has no 2 to the power of O small of n time. So as I said, it's ETH used now a lot in research. And now then later with other mostly other courses, we proved that because you see the first algorithm from 2014 was exponential space and somehow worked with not always good in practice. Now, so what we did, we introduced a backtracking algorithm which has polynomial space and also has the same running time, but it's much faster in practice. And now let me present you with computational experiments, starting from the next slide. And so here the number of users is 10 times the number of steps, and steps are from 10 to 60. And non-unary constraints of 3 types. First type is we have k constraints, at least 3 out of 5, which means that for 5 steps, we want to have at least 3 users, this diversity constraint. Also k at most 3 out of 5 means that for, again, size 5 of steps, we want at most 3 users. And finally, non-equals. These constraints where, for 2 steps, we want different users. And we choose E number of this, E of such constraints. How we choose this E? We choose them such that the probability of an instance to be satisfiable is approximately 50%. And we identified that those are hardest instances in practice because we saw fast transition happening for this in this case. Now we also our computation shows how fast this algorithm, our algorithm PBT, works for say unsat instances, which are generally harder to solve than SAT instances, satisfiable instances. And as you can see, in practice, it was a bit faster than 2 to the power of k log k, but you see quite apart from a coefficient in a similar time on average. So next, please. So now what we did, we compared a certain approach, certain algorithm. So first is this new algorithm, then new algorithm 2019. It's pattern backtracking, PBT, and it was implemented in C#, which is a couple of times slower usually than C++ code. And so the first algorithm was implemented in C++, so we cannot say that we got anything out of programming. Now, so we also compared with some solvers, this algorithm with some solvers. For example, we use SAT for Java and use some ordinary pseudo-Boolean formulation of WSP in the resolution proof system, because Gutin plain mode was much worse in practice. Then we used also SAT for Java and resolution for FPT formulation, fixed parameter tractable formulation, pseudo-Boolean formulation of WSP as alternative. And the next one is SAT for Java again used special fixed parameter tractable formulation with Gutin plain mode. And finally, in this slide, so if you move the slides, please. Yeah, so we also used CPSAT, which is from OR tools of Google, using ordinary CSP formulation of WSP. And so now what is ordinary pseudo-Boolean formulation of WSP? So here x as u equals 1 if and only if u is assigned to s, otherwise it's 0. And this also what we the constraints here, and we only have non-equal constraints, because otherwise it's too much to show. And first we assure that for every step we assign only one user. Also that it's 0 as x as u is 0 if you cannot possibly assign u to s. And also the sum of x s1u and x s2u is at most 1, because it's non-equal, we cannot assign more than one u to both or s1 and s2, right? So and then FPT formulation. What is this FPT formulation? We call it because it uses specifics of FPT variables, so-called FPT variables. So in this case, m of s prime equals 1 if s and s prime are assigned the same user, and 0 otherwise. And it's much longer formulation. Therefore, I'm not going to present it here. However, we proved the theorem which says that every non-binary UI constraints, user-independent constraints, can be encoded using these variables. So, and now basically what we got here in our experiments, as you can see on this legend, you see all these approaches, all these algorithms. And the red one is the new algorithm from 2019. So PBT. So the dotted lines are for satisfiable instances, and continuous lines are for unsatisfiable instances. And you can see a PBT performs much better than others. And don't forget that running times here are in logarithmic scale. So the actual winning is much higher than probably you can see it from this graph. So anyway, this is what you can see. And then this is when we fix the number of users. Now we fix the number of steps here, k 18, and then we varied the number of users, and we got a similar picture as well. Now, so all together, when we compared everything, the clear winner was this new algorithm from 2019, and runners up this CP-SAT from Google, solver of Google, and best of this resolution and cut-in plane modes, which used Fpt formulations, special Fpt formulation. Now, actually, in comparison, we can say that CP-SAT is two to three orders of magnitude slower than this specialized PBT algorithm and uses much more memory. On the other hand, if your instance is not too large, let's say, then it's CP-SAT is generally was sufficient, and as was told in one of the previous talks, because the solvers are getting improved year on year, so maybe it will be even more competitive over time. So now, what was remarkable about this CP-SAT of Google is that we used simply ordinary CSP formulation of WSP and not some special one. And nevertheless, when we see the results, the solver exhibited FPT-like behavior, so which was a bit unexpected to us. And then what is the explanation? We don't know, but the likely explanation is that as CP-SAT formulation is reduced to a SAT formulation, as part of the solution, and somehow the solver discovers this FPT variables and uses them. Now, let me tell you a little bit about some more advanced WSP stuff. So valued and by objective WSP. Now, so we introduced valued WSP in SACMAT, this symposium on access control, 2015, got best paper award for it. So, so here what the idea was that, okay, sometimes W instances are not satisfied. What to do about that? Well, in practice, perhaps we can falsify soft constraints, not hard constraints, especially if they are not falsified too much. For example, if you take a constraints at most 3 out of 5, only 4 users might be tolerated still, but 5 not really. So therefore, falsifying is not too much is maybe all right, but not. Now, formalization is this: for each constraint C and plan pi, if pi satisfies this C, then the weight of pi for constraint C is 0, otherwise it's positive, and we want to find this pi such that the sum of the weights is minimum. Now, here we introduced also UI constraints in valued WSP. They are basically constraints for which if two plans are equivalent, they are obtained from each other by simply permuting the users. Then their weights are also the same on the same constraint. And so for them, we also obtained the same running time algorithm, at least asymptotically the same running time algorithm, if all non-unary constraints are using independent constraints. So it's still FPT. And then we considered for the journal version of this paper, we can see that even harder kind of problem by objective WSP. So so this approach, by the way, was used. The approach which we introduced was used later by Curry and others published in SACMAT 2020, and they work for some corporation in the USA, and they used basically our approach for slightly different problem, how to optimize certain process in their company, such that they choose Pareto front, some solutions from Pareto front, and then give it to users, to give it to some people who can choose whichever solution they prefer. So it was introduced in a company. So now, if you take, so in our approach for WSP, we choose, we distinguish between unary constraint C1 and non-unary constraint set of C2. And then we found weights for each type of constraints for pi. So, and all sets and all constraints in C1 and C2 separately. And then we found Pareto front for each of this, for the problem. Pareto front are basically points where you cannot improve both objectives, both weights. They are kind of, if you want to improve one of them, then you will get worse the other one. And so we found we want to find all solutions like that, all Pareto front. And what turned out to be interesting that, yes, we can find all Pareto front for this problem and still get the same running time algorithm in asymptotically. And then we did some computational experiments. So here we compared our algorithm with the paper, pattern, branch and bound, and compared it to Simplex 12.6 at the time. And similar, K was a number of steps from 20 to 35, a number of users 10 times larger, and 1 hour per instance. And our algorithm solved every instance for K at most 30, and large majority for K equals 35. And Simplex solved all instances for K equal 20, and for K equal 35, less than 43%. But again, as was said before me, that the solvers are improving all the time, so maybe the picture would be a bit different today. Now, so what I want to say a few words for practical computing here. So, so first of all, fixed parameter tractable algorithms may be quite useful in practice. Not all of them, I should say. I worked a lot on FPT algorithms, and a lot of them are purely theoretical. But this our research shows, and not only for these problems which I told you, but some other problems. I don't have time to mention those as well. All problems from access control. That's where we focused. But they also turned out to be useful stuff. This sort of algorithms and even solvers for problems which are FPT showed FPT behavior, FPT-like behavior. So we know that even with solvers, you can solve certain NP-hard problems, and you know that it will not take that much time as maybe in general. Now, so what the next thing is that if an NP-hard problem is FPT, off-the-shelf solvers may be made more efficient if some variables used in constraints correspond to parameters. So that's for some solvers. So others, perhaps like this Google one, it's not even needed, maybe for some problems. Some problems, and that's the last thing, is some solvers may take advantage of FPT hard problem being NP hard problem being FPT without any help from the users. So somehow they're designed in a way that they basically recognize this and use it. So our current trend is basically to use more off-the-shelf solvers rather than specialized algorithms, simply because we understand that in practice, it's not so likely that the companies are going to unless it's a very, very important problem, they want to spend many weeks, implementing a specialized algorithm and so on. So that's basically it. I tried to do it fast, maybe too fast, I don't know.
Thank you very much, Professor Gutin. It's fascinating mathematical problems to solve, and then you explained really, really well. Like I said before, if you have any questions on this particular talk, please do email Professor Gutin. So could you also put your email into the chat box so people can reach you?
Right.
Okay, so
Professor
thank you very much.
Thank you very much for your help.
Thank you.